Everyone, PCB inspection is critical in electronic manufacturing. However, due to the large size of PCBs, a single image cannot capture the entire board. Have you ever wondered how to accurately stitch together multiple overlapping partial images of a PCB into one complete and clear image? Today, we will explore the principle of PCB image stitching and apply technologies such as the SIFT algorithm to solve this challenge, laying the foundation for future study and work. This lesson primarily covers the following topics. It is hoped that through this lesson, you'll be able to attain the following learning objectives. 1. Basic concept of image stitching. Image stitching is the process of combining a series of images with overlapping regions of the same scene into one complete image so that the stitched result closely approximates the original scene with minimal distortion. Based on the SIFT algorithm, the system maintains invariance to image rotation, scale changes, and brightness variation, while also achieving a degree of stability under changes in viewpoint, affine transformation, and noise. 2. Overview of image stitching experimental procedure. This experiment uses the SIFT matching algorithm to extract image feature points, employs the random sample consensus algorithm to solve the homography matrix, and eliminates incorrect matches. Finally, images are fused using the weighted averaging method. The specific processes are: first, 2 frames of images with overlapping regions are selected as the reference image and the image to be stitched. The SIFT matching algorithm is used to detect and extract feature points and compute their descriptors. Based on the similarity of the descriptors, matching feature point pairs are determined. These pairs are then used to calculate the homography matrix of the image to be stitched relative to the reference image, which is used to transform the image accordingly. Lastly, the 2 images are fused to form the final stitched image. 3. Detailed experimental steps. 1. Feature extraction. Feature points are extracted from each image to be stitched. These feature points should possess distinctiveness and stability, such as corners or edges. Common feature extraction algorithms include SIFT, Scale Invariant Feature Transform, SURF, Speeded Up Robust Features, and ORB, Oriented Fast and Rotated Brief. For example, SIFT constructs a difference of Gaussian pyramid to detect extremum points in different scale spaces as feature points and calculates descriptors that contain gradient information from the surrounding region of each point, effectively characterizing their properties. 2. Feature matching. This step involves identifying corresponding relationships between feature points in different images, that is, determining which feature points represent the same object or position in the real-world scene. Common matching methods are based on distance metrics, such as calculating the Euclidean distance or Hamming distance between feature point descriptors. The smaller the distance, the more similar the feature points are, and thus a match is confirmed. For instance, the ORB algorithm uses Hamming distance to quickly match feature points. Everyone, the feature matching step builds correspondences between images by calculating the similarity between descriptors. This process demands extremely high precision, as even a minor mismatch can cause the entire stitched image to appear with ghosting or misalignment. This reminds me of a real case from a medical device R&D team. When developing an endoscopic image stitching system, early prototypes showed misalignments at vascular bifurcations in gastrointestinal mucosa images. Initially, engineers attributed this to algorithmic limitations, But clinical investigation revealed that the issue lay in viewpoint variation. Subtle tremors in the endoscope lens caused nonlinear deformations of vascular textures, which the traditional SIFT algorithm, assuming a rigid transformation model, could not handle this physiological deformation. Instead of simply upgrading the algorithm, the team adopted a collaborative development model between engineers and clinicians. They created a clinical feature database with annotated anatomical markers like vessel bifurcations and mucosal textures. They then developed an elastic deformation compensation model, incorporating physiological characteristics into the registration algorithm. This approach achieved a matching accuracy of 0.9 pixels after dynamic simulation validation. This case teaches us that technological optimization must not detach from real-world application. Feature matching, while mathematically rigorous, must also account for practical constraints. In scientific research, we must respect technical rigor while fostering cross-disciplinary collaboration to ensure innovations truly serve real needs. 3. Image registration. Based on the feature matching results, the transformation relationships between images, such as translation, rotation, and scaling, are calculated to align them within the same coordinate system. A commonly used method is the calculation based on the homography matrix. By minimizing the reprojection error between the matched points, the homography matrix is estimated. This matrix describes the transformation relationship between the two images. For example, in panoramic image stitching, homography matrices between adjacent images are used to transform them onto the same plane. 4. Image fusion. The aligned images are fused, and overlapping regions are processed to ensure natural transitions and seamless integration in the final image. Common fusion techniques include weighted average fusion, which assigns weights based on the distance of a pixel to the boundary of the overlap region and calculates a weighted average. Another method is multi-resolution fusion, which decomposes images into different resolution levels, performs fusion at each level, and then reconstructs the final image. For example, in weighted average fusion, pixels closer to the boundary of a particular image are given higher weights from that image, resulting in more natural visual transitions. Everyone, this concludes our lesson on the principle of PCB image stitching. Through this course, you have mastered the key techniques of image stitching. In future studies and work, you will face many technical challenges. Just like resolving stitching errors, as long as you maintain a spirit of rigor, continuous exploration, and innovation, you will overcome obstacles and contribute to the development of industries like electronics manufacturing, achieving both personal and societal value.